Welcome to our HopsWorks webinar J0927, the fastest NewSQL database and only feature stored database. Today, we will cover J0927's key features and give you a technical overview. Our speaker, Dr. Mikael Rangström, is a world-renowned database expert. At Ericsson, he founded the NDB cluster acquired by Oracle, now with 40,000 installs worldwide. Mikael joined HopsWorks as the head of data and forked the NDB project to modernize it. I am Nathan Greenhut with 20 years experience in data and AI, and I am the head of accounts at HopsWorks. In a world where machine learning is increasingly driving profits, companies are turning to J0927 and HopsWorks to power better, faster, and cheaper ML-driven apps. J0927 is the fastest NewSQL database and never stops running. J0927 is the only data platform that meets all of the requirements listed here. J0927 is the only purpose-built for machine learning features database and covers all modern database requirements and is a part of the HopsWorks Polyglot platform. J0927 covers a number of mission-critical real-time use cases. Today, we will cover the online feature store use case listed in the top left of this slide. In a world where ML models are increasingly driving corporate profits, our data platform is better, faster, and cheaper. ML models are powered by what data scientists call features. For those of you on the webinar that have not heard of features before, features are inputs to models. They are the key columns of data that have predictive value. They can come from any data source, such as Oracle, Snowflake, Spark, HDFS, Mongo, or Neo4j. With J0927, we offer better predictions with consistent features and fresher data. Faster development, we're always running, and we have the ability to meet regulatory requirements. Now, Mikael will walk you through key features and a technical overview of J0927.
Okay, thank you. So in the feature store database, there are a number of things like the online store. That's when you want to do your predictions. So the online store is about, for example, let's take an example. We have Spotify, for example. They might have a search capability in their application, and when you want to search, you want to use AI to do a good search based on the user's preferences. And to do that, you require feature data about the user. And that data has been generated by training data and sort of feedback from the user and what the user has been up to. And so the online store contains the feature data that's required to do the predictions. The offline feature store is where you store all the feature data historically. So that's where you have your training data. So that means that in the offline feature store, you run your training, and then you store the feature data in the online store so that you can do the predictions. But however, features requires also a lot of metadata. So for example, in HopsWorks, we group features into feature groups. And effectively, a feature group could contain hundreds of different features. But in reality, your application might want to have features from many different feature groups. So you might want to have 10 features from one feature group, 10 features from another feature group, and sort of merge them together. So in the same way as a database has views, we have feature views that gives you views over feature groups. And so the feature store, and in order to to know what what features belong to which feature views and which feature groups and so forth. You have feature metadata. So that means that in a database that works with features, we have three different stores. We have the online feature store, we have the offline feature store, and we have the metadata feature store. And all of those have to be capable and running. And then we have, of course, also models, registries for models. We have access control, provenance. It's very important to keep track of how do you actually derive the features? Where do they come from? In the world where copyright, for example, is very important, it's very important that you have a sort of knowledge about how you actually derive those features. Did they come from a place where you actually had the permission to use those features? So there are lots of things like that that you also have to store in the feature store. So moving on to the next slide. So this slide here shows a little bit about the HopsWorks feature store. We also call it the HopsWorks data platform because you could actually use exactly the same architecture for also other applications, not just for a sort of feature store. But this is the architecture of a feature store. And it fits also with many applications that enterprises have. So you can see here you have a data pipeline that comes from a lot of different places. You have data coming from Kafka, Flink, Beam, and has been put into Kafka, Flink, and Beam from sort of any other source. You can get data directly from a data warehouse like Databricks, Snowflake, BigQuery. You can get it from a database like Oracle, MongoDB, MySQL, so forth. You can get it from big files, CSV files, Parquet files, and you can even map even existing tables from different databases and connect them to the HopsWorks feature store. And you can either so you can have a pipeline of streaming data going into this set of data. And so data goes, the online data goes to the online data store, and the offline data goes to the offline data store. And then you have the metadata in the middle. And then all of this is used to train your models and finally to do predictions. Okay, moving on to the next slide, I'll show you how this system actually has the HopsWorks data platform, or the HopsWorks feature store has a number of components. So we have the online data store or online feature store, dependent on if you want to use it for features or if you want to use it for any other data application. It's built on RomDB. So this is a very important part of the architecture because RomDB provides the highest availability, the lowest latency, the highest throughput, so meaning that you can have your data being changed very often. You can have data delivered to you very quickly and at a very high availability. As an example, RomDB is built on top of NDB cluster, as mentioned, and one of the customers of NDB cluster had hundreds of clusters up and running for 10 years without any downtime. Then, of course, human beings are human beings. So every now and then there is, of course, always a problem because there is no such thing as a perfect human being. So as you're probably aware of. The other part, the offline feature store or offline data store is handled by HopsFS, which is a distributed file system. This distributed file system is using RomDB again in the metadata layer. And then the actual files are stored on HopsFS data nodes. On top of HopsFS, we have Hoodie, which is a data lake. So that gives us the possibility to do extremely scalable analytical queries on the offline data. So this is obviously very useful for training, for things like that. But we also integrated DuckDB in HopSworks data platform. And DuckDB is like a very, very fast analytical database. So we have the best of both worlds. We have the fastest key value store, and we have the fastest analytical database as well in the HopSworks data platform. So DuckDB is extremely fast on doing analytical queries. It is, however, limited to sort of memory size. So that means that Hoodie is a useful thing if you really want to do really huge things where you want to do scalable queries. And then again, we have the data store metadata layer or feature store metadata layer. And again, this is built on RonDB again. And so as you can see, RonDB is a very important part, but we use components wherever they are best fitted. And finally, we also have, of course, a search layer. And modern databases also have to have a vector database index, or in the feature store world, this is called embeddings. So an index of embeddings in the feature store. In the database world, it's called vector database index. And it's built on OpenSearch. So the idea is that we store the vectors in OpenSearch. So whenever you need to query the vector index, you go to OpenSearch, you get the vectors that are close to your search criteria. And then you go to RonDB to evaluate each of those vectors to see sort of which of the vectors does actually fit best with my model. So as you can see, we have solutions for all parts of your data management in the HopSworks data platform. So moving on. So this shows the architecture of RonDB, the RonDB part. So we have MySQL servers that you can access. We also actually have REST API servers. So we do have a REST API towards RonDB. We have the management servers that take care of configuration and things like that. And the actual data resides in those node groups. So we can have one or more node groups. Each node group is fully replicated. The data in each node group is fully replicated. So you could see the node groups as shards in a sense. So in this case, for example, there are 2 shards or 2 node groups, and there are 3 replicas in each node group. We could also run with 2 replicas, and it's just fine. Okay, so that, moving on. So this shows how you can also use RonDB to set up regional replication. So if you want to have a data platform that covers the needs of enterprises, the first thing that you sort of realize is that in order to get the highest availability, you need to have it reliable, even if a whole region goes down. So this was something we saw early on with telco customers of NDB, and it's the same thing for HopSworks customers. So we have in production customers that need to have multi-regional applications of HopSworks. So the way one important part of the solution for that is to use regional replication. So in the RonDB case, the primary site will update in the data nodes of RonDB, and those updates will be propagated to MySQL servers that are responsible for replicating to another cluster. And there is an active channel and is a backup channel. So there also this part of the replication is also highly available, so that if one of the replication channels goes down, you can always switch to the other. Okay, moving on. Now, if we look at the HopSworks feature store, in the HopSworks feature store, the online data comes from Kafka and uses a application called Online FS, Online Feature Store. So the data that comes from could come from any kind of place, are placed into Kafka, and then they are propagated into the RonDB cluster. So we worked hard to make sure that the time it takes from that you send things from the original data source into that it should be a very, very short time before it reaches the RonDB so that it can be part of the predictions immediately. If you have a multi-regional setup in this case, what we do here is that we update the online feature store with the same data. So it's an active. So both of them actually have all the data that you require to do your predictions. So this is the way we solved it for the HopsWorks online feature store. Moving on to the next. So the metadata layer, however, has a different solution. In the metadata layer, what we can write to both HopsWorks applications in both the primary and the replica region. But if you write to the replica region, the write will actually be forwarded to the primary region. And so the actual update happens in the RonDB cluster in the primary region. And then we use this asynchronous replication towards the replica region. You can still read the metadata in both the primary region and the replica region, but it's active passive in the sense that all the updates goes through the primary region. Actually, with RonDB, it's possible to write active also in this case, but then you would have to treat conflict. You would have to handle conflicts. And RonDB does have a few, like 5 or 6 different ways of handling conflicts. But it's obviously, in most cases, enough to have active passive in this particular case. So this is the globally replicated metadata layer when you are running in a sort of multi-regional setup. So moving on. And the final thing is that you also need to have the offline feature store or offline data store also has to be replicated over regions. So the metadata of HopsFS is stored in RonDB clusters. So it uses asynchronous replication in the same way that the metadata layer uses it. And then you have a cluster arbitrator that could be more or less, it could be an automatic application, but it's probably more like a manual thing. It's a web server that could respond to a JSON request and send a JSON that tells you which region is currently active. So HopsFS will do all the updates and so forth in the primary region, and then the updates will actually go to a object storage, and that object storage is actually multi-regional as well. So most enterprise companies, if not all, already have that kind of capability. So we're building on top of that capability. We're building a sort of distributed file system that has regional replication in it, both for the metadata and for the actual data. So as you can see now, what we have shown is that we have a HopsWorks data platform. We use this for the feature store, but we can also use it for many other types of applications. So we're talking to customers also about how to use this in other areas where it's not machine learning. So we focus our efforts obviously on the feature store, but we can also use the same data platform for very, very many other application types. And it fits very nicely, the offline and the online, and having lots of data that you want to analyze. And then, of course, you want to have your online application highly available, low latency. So now we will move on to looking into what is it that the online feature store can bring. I mean, the RonDB part. So the first thing that we have full availability during recovery. We have full availability during continuous integration and continuous development. So you can update your tables, you can drop your tables, you can update the data, and you can do a software upgrade, software downgrade. All of those things you can do without any downtime. We have a tiered storage, so you can choose to store all your data in memory if you want. We also have a hybrid solution where you store parts of your data on disk. So with current disks, we actually can do that with pretty good both throughput and latency. Obviously, in memory will still be at least 2-3 times faster and probably 2 or 3 times lower latency. But if that higher latency and lower throughput is okay, given 10 times cheaper storage, then sort of disk columns are still a pretty good idea to use in many applications. But it's your choice as an application developer where you store your data. We have scalability on reads. We have also scalability on writes. It's very, very high throughput. We haven't seen anyone that beats it on performance yet. We have security. We have ease of use. I mean, it's based on MySQL, so it has all the APIs that MySQL have. On top of that, it has all sorts of other APIs. There's even lots of applications using LDAP on top of RunDB, and we can build graph databases on top of RunDB. We can do all sorts of things on top of RunDB. We also have a distributed sharded serverless application. Currently, it's a feature store. So anybody that wants to try out the HopsWorks feature store, they can go to app.hopsworks.ai, if I remember correctly, and they can do their own machine learning application, running that for free and try out the HopsWorks feature store, which obviously also means that we have a RunDB serverless as part of that solution. So it's basically the HopsWorks feature store as a serverless feature. And we have the lowest latency. Okay, moving on. So I'm going to go through most of those things in separate slides, but I'm going to talk a little bit more now in detail about performance, read scalability, write scalability, ACID compliance, and so forth. So let's dive into the details. And so it's also going to cover availability, security, low cost, and continuous integration and development. So moving on. So performance of the online feature store. So we have a very high throughput. Already 10 years ago, NDB cluster showed a benchmark where you could do 200 million reads per second. I mean, it's so breathtaking that we haven't seen any particular need to update the benchmark, because so far I haven't seen anyone even go beyond 100 million. And this was 10 years ago. So you can imagine that if we did the same benchmarks today, we'll probably go into the billions of reads per second. And at that time, we also did 20 million updates per second. So the throughput is sort of beyond any type of requirements that we've seen in the market. So we'll definitely meet the performance requirement when it comes to throughput. Latency is, however, more important maybe. So when we do our primary key lookups, it takes part of a millisecond. So for example, if you run in a small environment where the nodes are close to each other, you can definitely get it to be below 100 microseconds. If you run it in a bigger environment where it's a little bit more space between the nodes, maybe you can say it's like in a cloud environment, you would probably have like 200 microseconds. The good news, however, is that in most applications, you actually want to read more than one row. So for example, in the telco space where NDB grew up, very often you start with looking up one row, and then based on that row, you look up 15 other rows. So obviously, it's very important to also support batched key lookups in a small number of milliseconds. And the good news is that you can do hundreds of primary key lookups and still have them return in a few milliseconds. We also have something called left outer join. So if you can actually push down a left outer join. So for example, if you want to join 10 tables together based on a primary key, in essence, it's like reading 10 tables in parallel. But in MySQL, this is pushed down to the data nodes and becomes much more efficient than if you did 10 SQL queries reading the 10 tables. And you can do that again in less than a millisecond. You can get the results of a join from 10 tables. We also have implemented a REST API to do things like this. We have a Flink and Kafka connectors for streaming data. If you're running in a sort of in a number of availability zones, we can set up the configuration such that you always read the nearest copy. So if you go to another availability zone, it's likely going to be like a jump of 400 microseconds or more. And so it's much, much better if you can read the copy that resides in the same availability zone from where you sent the request. So that can give you like 10 times faster latency. And similarly, you might want to, if you have a multi-regional, you might want to read the data in the closest region rather than going to the primary region. Okay, moving on. So read scalability. So we do scale horizontally for reads. So it's as mentioned, the data is sharded on the partition key. And we automatically route the reads to the nearest copy in a multi-availability zone region setup. We also, inside the data node, we also do routing. So actually, we have a very advanced sort of threading concept in the data nodes. So some of our competitors have tried to copy what we're doing, and they're at version 2. We're already at version 4. Of how you sort of implement a sort of efficient thread concept for a key value store. And so what that means is that we have the capability to sort of to route the reads to the least loaded thread. So in a sense, you could say that the RonDB data nodes is almost like an operating system that contains scheduling of things so that we make use of the CPUs in the most efficient way, and we take into account where we have the CPU caches and all of sorts of things like that. We do also have I mean, if you have your data in your online data and you want to do a little bit of analysis, obviously RonDB is not a sort of it's not an analytical database, but it does have a possibility to do small queries that joins together a lot of tables and can automatically parallelize that query execution. So you can easily get the query that is parallelized into 10 different thread executions and be run very efficiently and very fast for certain queries that fit your needs. Okay, moving on. Obviously, the read scalability is good. We also have similarly very good scalability for writes. Again, based on the fact that we shards on the partition key. Whenever we write, we always write all the nodes inside the data owning node group. So every row in the database is stored in one of the node groups. So it's an important concept that we store things in node groups, because that's the best way of achieving the highest availability. It means that if you have one node in your node group that still survives, you can still be up and running. So if you have your data spread in a more or less random way, and you have 2 replicas, well, after 2 crashes, you're bound to be offline. So basically, you have some data that you lost. So you can't really be up anymore. With Rendezvous, if you have 2 replicas and 4 nodes, you can have 2 nodes crashing, 1 in each node group, and you're still up and running. And we can even run with 2 replicas based on the fact that we use a concept called arbitration. So you still need to have 3 nodes to find out whether you can avoid a network partitioning. But the 3rd node doesn't need to be a data owning node. It can be basically any node that just gives a vote. When we start a transaction, we already know what the first data item is. So that's where we're going to place the transaction coordinator. So in most cases, what that means is that we have the transaction coordinator very close to the data, but we still have full support of distributed transactions. We also have, as I mentioned already previously, parallel load facilities like the online FS, but we also have capabilities like NDB import, NDB restore, which is restoring a backup and things like that. So we can load data very quickly into Rendezvous. The biggest test I've done was a single data node that had 5 terabytes of in-memory data. And that was storing 53,000 warehouses in a TPCC benchmark, which is essentially 5 terabytes of data. Okay, moving on. So, between Rendezvous clusters, the replication that we use is based on something called epochs. So what that means is that we gather a number of transactions together and call them an epoch. And that epoch is basically consistent. So that means that once we have replicated that epoch over to the other side, all of the transactions in that epoch is part of the replica cluster. And we do have active passive replication. We have active passive replication with failover, and we have active replication also using conflict detection. Okay. So we have ACID support. So ACID stands for atomic, consistent, isolated, and durable. The atomic, we get that through a 2-phase commit protocol. And so some people, when they hear about the 2-phase commit protocol, they think, oh, that's blocking. But that's, however, not true in our case, because we have a coordinator, and if that coordinator fails, we will finish the transaction still by using a takeover protocol at node failure handling. We do have consistency through row level locks. So that means that as long as you lock on rows, you can actually get a serializable execution and isolation level. But we don't have, it's a distributed system, so we don't support range locks or anything like that, because it's more or less, well, it's actually, I mean, so, but we do have row level locks. So in effect, if you have a need of a consistency or isolation levels that goes beyond what Rendezvous supports, you can always use row level locks to sort of to for example, a row level lock could be a table lock if you manage to write your application in such a way. We do also persist transaction to disk media so that if we have a full crash, we can still recover because all the transactions goes to disk as well. And they go to disk with the same epoch consistency level that we have with replication. And also, whenever we create the table or create an index, drop an index, and so forth, those changes are atomic. So either the schema change succeeds or it doesn't succeed. So all the schema changes are atomic. Okay, moving on. HopsWorks is ISO 27001 certified. That means that we're certified to store and handle data of our customers. And HopsWorks is also SOC 2 compliant, SOC 2 Type 2 compliant and certified. We have at rest encryption. We have in-flight encryption also very soon. So security is something we look at in a hard way and try to solve. Yeah, moving on. So availability. We get 6 nines of availability with region-to-region replication. And the only reason why we don't reach any higher than 6 nines is because we work with humans. And humans tend to do mistakes every now and then, so it's almost impossible to build. It's impossible to build a completely fail-safe. But basically, you could say that the HopsWorks data platform is about as sort of highly available as you can build them. I mean, when I used to work at Oracle, Larry Ellison used to brag about the Oracle database having 5 nines. He didn't obviously know that he had a database inside of Oracle that already had 6 nines. So 5 nines wasn't much to brag about. 5 nines is what you get within a region, because if in order to get to the 6 nines, you need to have region-to-region replication. There are some cases where, for example, you have to do very complex application changes that you can do that perfectly fine with region-to-region replication, but without that, in a single region, you would still have to do some downtime in a very complex application change. Okay. So columns can be stored in memory on disk. On disk is obviously like 10 times cheaper, but as mentioned, it's a higher latency, it's lower throughput. So for optimal performance and latency, obviously in memory is best, but very often cost is an important driving factor as well. So we have the on-disk solution for the cost-based solution. And for example, in a feature store, it's very natural. I mean, you basically have a number of columns that you know that you're always accessing, and those can be in memory, but most of the columns are basically just like payload data that you put into some other application. And so it doesn't sort of hurt performance a great deal to store those on disk, and which means that you can have a feature store with petabytes of data even in the online feature store or online data store. So even there you can get up to petabytes of data, which is kind of remarkable. Yeah, go on. So here is a list of the different interfaces that you can use in the HopsWorks data platform. You have MySQL APIs, you have the C++ NDB API, you have a Java NDB API called ClusterJ. There's even a JavaScript NDB API called Node.js NDB API. There is even a community user that's developed a common Lisp NDB API. We have an open LDAP extension. The common Lisp implements an RDF database on top of RonDB. We have a REST API for sort of web applications. We had Flink NDB. It's developed at KTH. We have a Kafka service in HopsWorks. We have Spark integrated in HopsWorks, and we have the HopsFS distributed file system built on top of J0927. Okay. So in RonDB, we have automatic load balancing inside of the data nodes. So the new transaction always starts on the data node owning the first row used. And we even go to the primary replica of that particular row. So write operations will be sent to all alive nodes in the node group. Locked reads always are sent to the primary replica because we do primary copy locking to avoid getting problems with deadlocks. Read committed will be sent to the closest replica, and read committed actually doesn't require any locks because read committed simply reads the latest committed value. And internally in the data node, we balance the load on the internal threads. And this rebalancing happens thousands of times every second. So it's kind of interesting. It's even a philosophical thing to develop something like that, because you have to really consider time as an important part of the architecture. Okay. We do have 12 dashboards with different graphs that we can use to monitor RonDB. We have automated failure detection. So if something goes wrong, we automatically fail the system, and we also automatically recover the system. And we have built a managed RonDB solution where you can basically add and drop MySQL servers as you like. You can even add and drop data node replicas. You can increase the size of VMs for all VMs in the RonDB cluster. And you can change the software online. So all of those things you can do automatically in a managed RonDB setup, and this managed RonDB is part of the HopsWorks data platform. So something you get as part of the platform. Okay. So global replication, I already mentioned that a few times, so it's probably, so we can move on. So just to sort of show you how multiple failures we can support that. So here we have a setup where we have 2 node groups. We have 3 replicas. We have the arbitrator running in, for example, the management server. So in this particular setup, any kind of single failure, we will survive. In effect, we will actually survive any failure of 2 nodes in this setup. So even 2 nodes in the same node group. If 3 nodes goes down at the same time, we will survive anything except if all 3 nodes of one node group fails. That's the only case we will not handle with 3 failures. 4 failures still will be too difficult, because then we cannot even get the majority of the nodes. So that we cannot handle, but we can survive in this particular case up to 3 replicas failing. If we have a failure of 3 replicas, like for example, if 1, 2, and 4 fails, there is obviously a problem. What if we had a network partitioning and 3, 5, 6 also wants to build the new cluster? That's where the arbitrator comes in. So the arbitrator only comes in when there is a debate whether the surviving cluster can be the only cluster surviving. So that means that it's only in the case when we have 50-50. And obviously, if all nodes of one node group has failed, then that sort of, you cannot continue. So in that case, you might not even need a majority. But in the case where it's a 50-50 decision, that's when the arbitrator comes in. So let's assume that both of the partition cluster manages to contact the arbitrator. Well, the arbitrator will only say yes to one of them. He will say no to all the ones coming after. So that's the only thing that the arbitrator does. He answers the question with yes or no. Yes, you are allowed to continue. No, you're not allowed to continue. And if the no comes, then that part of the cluster will be automatically shut down. Okay, moving on. So let's now assume that we started with one node group with 3 replicas. And now all of a sudden we want to scale up. So we want to have 6 nodes with two node groups, 3 replicas still. So we add 3 new data nodes. And obviously that means that we have twice as much memory, twice as much CPU power, twice as much disk. So what we do there is that we have a command called add node group. So it's a very simple command. You add the nodes and then they are there. However, there's no data in those nodes. So in order to move the data from the first node group to the second node group, we have to redistribute rows. And we do that one table at a time. So you write an SQL command like alter table, reorganize partitions, and then you reorganize the data so that half of the data will now be in the new node group and half of the data will remain in the node group 1. So all of that can happen while your system is up and running in the middle of the daytime when everything is happening. So there is a little bit of extra load, but for the most part, you can do all the things that you do in normal operation. You can do that while you're increasing the size of the cluster. And there is no downtime for neither updates nor writes. Okay. So DDL operations and software upgrade, we can handle add column while writes happen. We can add and drop indexes. At the moment, we cannot drop a column. So this is one typical example of if you want to drop a column and do that as an online operation, then that's where regional replication comes into play. That's the type of there are things like that could still be useful to have regional replication in order to get the very highest availability. We can perform software upgrade and downgrade while writing, and it's an online operation. So it's basically a rolling restart of the cluster. Okay. So that concludes. So as you can see here, we have sort of a feature store that's very capable to handle all the sort of requirements that you have on a machine learning platform. So HopsWorks is a platform that can be used for feature stores, for model serving, for model registries. So we can use it for global design, anti-fraud, money laundering, credit risk, identity and access management, distributed payments, gaming. We can use it in the telco space, personal recommendations, and you can use it for many, many other things as well. I mean, it's a data platform that basically supports all the things that you need in your data pipelines and your use of your data so that you can do the things that your company requires best. And as we also saw, all of this comes with an enterprise setup where you can even do regional replication. So even the very biggest companies can use this platform for their very biggest applications and the most important applications. I mean, in the telcos, for example, every time you make a phone call, you're likely to use NDB cluster because most of the databases that takes care of the data in your mobile phone networks, they actually run on top of NDB cluster. So there are like 5 billion phones relying on NDB cluster. So you can rely on RonDB and Hopsworks data platform for your application, I can assure you. Okay. Great, thank you.
Mikhail, thank you. And to all of our attendees and guests today, thank you for joining our webinar on J0927, the world's fastest NewSQL database and only featured database. If you want to reach out to us to contact us, I posted the Slack community and then also our website. There's a contact us. I also posted YouTube videos, a link to the YouTube videos and prior webinars, and then also to our GitHub if you want to start using some of our code that's open source as well. Should you want to reach out directly to Mikhail or myself, please email me at the contact information at the bottom of the page, nathan.greenhut@hopsworks.ai. Thank you, everybody, and enjoy the rest of your week.